Hello and welcome to BSides Vancouver 2021. This talk is Securing Kubernetes in the Cloud. My name is Amiran Alavidze. I'm currently Director of Security at TestUp. We're a Vancouver-based startup helping companies succeed in their digital transformation journeys. As security professionals, we're often thrown into something we have no idea about. Often it's a new tool that your company is deploying and you need to figure out how to do it securely. To me, dealing with these unknowns and reasoning with limited information is a feature, not a bug, of a security role. Similar thing happened to me with Kubernetes. We decided to use it for hosting one of our sales products, and at the time I knew pretty much nothing about it. And here we are a couple of years later with me being a certified Kubernetes administrator and presenting on the topic. This talk is the amalgamation of many months of learning, threat modeling, and incrementally improving security of our production Kubernetes clusters. And by sharing this, I hope you'll be able to benefit from our experiences. Let's start by understanding what is Kubernetes. Kubernetes is open source container orchestration platform originated at Google from their internal project called Borg. It's been designed from the ground up as a loosely coupled collection of components centered around deploying, maintaining, and scaling workloads. It has good support for declarative deployments and immutable components. Let's cover some core terminology. Kubernetes is a container orchestration engine, so it all starts with containers. Containers are deployed from images, which essentially are templates for running containers. But in Kubernetes, the smallest deployable unit of computing is not containers, but rather pods. And pods are one or more containers that are deployed together on a single host. Those running containers and pods will often need configuration information and credentials to be able to run, and those are injected through config maps and secrets. To access the pods from outside, you would deploy a service, and then to horizontally scale those workloads, you will deploy a deployment which will specify how many instances of those pods do you need. All of these resources can be logically grouped into something called namespace, and a lot of the Kubernetes control plane processes will also run as part of the cluster in the kube system namespace. Let's spend some time understanding Kubernetes architecture. You can find this diagram in Kubernetes documentation. The cluster consists of one or more master nodes and several worker nodes. Master nodes are responsible for running Kubernetes control plane processes. In the Kubernetes control plane, we have etcd, which is a data store for the cluster. We have Kube API server, which is a REST API for cluster management, and essentially is a front end of the cluster and all the other components running as part of the cluster interacting with the cluster through this API server. We have Kube Controller Manager that runs multiple control processes in a loop, and we'll talk about those in just a bit. There's Cloud Controller Manager that's responsible for interfacing with infrastructure as a service cloud providers if the cluster needs any resources provisioned in the cloud, such as load balancer. And there's Kube Scheduler, which determines which pods should run on which nodes. On the worker nodes, we have Kubelet, which is responsible for provisioning, starting the pods that are scheduled on that node. And so it interacts with the container runtime, such as Docker, on that node to do that. And it also reports pod status and node status back to the API server. And we have Kube Proxy, which is a proxy service responsible for routing network traffic to the pods on the node. We also have kubectl, which is a command line tool for interacting with the Kubernetes cluster through the Kube API server. It supports both imperative and declarative use, and YAML is mostly used for declarative definition of the resources in the cluster. To understand how all of this works together, let's hear a life story of a deployment. Let's say a cluster administrator creates a new deployment, usually using kubectl. That kubectl connects to the kube API service and tells it about the new deployment. Kube API service saves all of that information into the etcd database. And at this stage, kubectl returns back to command line. So now in etcd database, we have this deployment object that will contain all the information needed for that deployment, including name of the deployment, number of replicas, number of pods that should be executed as part of that deployment, and the images that should be used in those pods. Now, the deployment doesn't actually manage those replicas that are defined for the deployment. It only manages the lifecycle, essentially rolling into new versions of the images and things like that. So for managing the number of replicas, Kubernetes uses an object called replica set, which we haven't talked about before. So now one of the control loops in the controller manager comes along and finds this deployment object and doesn't see a corresponding replica set object, so it creates one. This replica set object will inherit the information that it needs from the deployment object. Now, another control process as part of the controller manager will come along and sees this replica set object, but doesn't see the corresponding pod objects, so it will create those. And the number of those pods that will be created will be a reflection of the number of replicas that have been requested for that deployment. And now a scheduler comes along, and the scheduler looks at all those new shiny pods and assigns them to specific node, essentially populating a node name property of all of those pods. It's important to understand that while this is all happening very quickly, but at this stage, none of the workloads are actually running in the cluster. This is all happening in the etcd database. What happens next is kubelets on the worker nodes will check periodically with the kube API server, essentially seeing if there's the desired state for them have been changed and if there's been new pods assigned to the nodes that that kubelet is managing. And when that API call is made, the API server will check with the etcd database and see and give the kubelet the information that it requests. And then kubelet sees this new pod that has been scheduled on the node that it's not running yet, and it will provision the containers that are required for that deployment, and this is how the workloads start. So why are we talking about Kubernetes in the cloud today? As you can see, Kubernetes is a complicated ecosystem. It's almost like a Lego-like architecture with multiple, somewhat independent projects closely working together. There's multiple ways to deploy and configure the cluster, which also means there's multiple ways to screw it up. There's also a number of things that need to happen outside of the cluster or as a cluster plugins. Things such as networking, horizontal or vertical node scaling, and also load balancing and or public to private IP address mapping. If there's only one thing you take away from this talk today, it should be that if you're just starting out, you probably shouldn't run Kubernetes on your own. Now let's talk about Kubernetes threat model. Going back to Kubernetes architecture, let's think about attack surface. We have potentially etcd, we have kube API server, and we have the worker nodes, because supposedly they're running your workloads in the cluster, and some of those workloads will be available from outside the cluster. So if we think about all of that, we have attacks on the control plane, we have compromised applications running in the cluster. Imagine a scenario of somebody hacking into one of the workloads, one of the applications that you run in the cluster, and now having access to the container that's running that application. We also have compromised user accounts and credentials, and those can be used potentially to access the cluster and compromise the cluster now. And we also have compromised images, essentially a supply chain risk applied to your environment. In 2018, CNCF that manages the Kubernetes project has done an RFP and selected 2 companies, Trail of Bits and Atreides Partners, to do a security audit for Kubernetes. I highly recommend you go back and read the document. They published the full audit report for everyone to see on the GitHub using the link on the slide. Out of those threat model scenarios, the main one to me is the compromised application running in the cluster, because that is bound to happen at some point of time. So let's explore that scenario further, and we'll talk about 3 main things here. 1, network access and lateral movement within the cluster. 2, Kubernetes cluster credentials. And 3, container escapes. Networking is not a core part of Kubernetes and is provided by third-party networking plugins, also called CNIs. At the core of Kubernetes is an open networking model. From Kubernetes documentation, Kubernetes imposes the following fundamental requirement on any networking implementation. Pods on a node can communicate with all pods on all nodes without net agents. Those networking plugins may support network policies, which is a way to firewall traffic within the cluster, but they're not required to do so. So if we have access to a container running as part of the Kubernetes cluster, potentially we might have access to the instance metadata endpoint, which is a way for cloud service providers to inject temporary credentials required by the nodes running in the cloud. And this, by the way, can also be exploited through SSRF type vulnerabilities and don't require full access to the container. We also might have access to the Kubernetes control plane, as Kube API server by default is exposed within the cluster. And we might have lateral movement in a traditional sense and be able to connect to databases and other services running as part of the cluster that are not exposed to the outside world. Another vector for lateral movement that's worth exploring is Helm. Helm is the package manager for Kubernetes. It allows you to deploy Kubernetes applications called Helm charts. There's 2 major versions of Helm in use today, version 2 and version 3. And version 2 requires you to run a service called Tiller within your cluster that has privileged access to the cluster and does the actual deployments. Your workloads might be able to access Tiller and might be able to leverage that privileged access within the cluster. And this phrase is from Helm documentation. Default installation applies no security configurations. Let's talk about cluster credentials. Kubernetes supports multiple authentication options, which include certificate-based authentication, token-based authentication, basic, and OpenID Connect authentication. But Kubernetes doesn't manage users within the cluster. They have to be defined externally. What Kubernetes does manage, though, is service accounts. And service accounts is a way to provide the workloads that are running as part of your cluster access to Kubernetes resources. Even if you don't create or specify service accounts, by default, every pod in the cluster will get assigned a default service account from the namespace where the pod is running. Kubernetes also supports role-based access control. Those are done on 2 levels. One is roles and role bindings that are scoped to a specific namespace, and another one is cluster role and cluster role binding that are scoped to the whole cluster. So role essentially defines the permissions that can be assigned to users and service accounts, and role binding assigns the role to a specific user, group, or a service account. Our third topic related to a compromised workload in a Kubernetes cluster is container escapes. Container escapes can happen in multiple ways: through container runtime vulnerabilities, through outdated kernel and kernel level vulnerabilities, through security configurations, things like mapping a Docker socket to within a container, mapping other sensitive paths from a host to a container, and assigning excessive capabilities to a container, as well as privileged containers and misconfigured UIDs of the running containers. I refer you to an excellent talk, A Compendium of Container Escapes by Brendan Edwards and Nick Freeman. I hope I scared you enough by now, so it feels like a good time to talk about protecting our clusters. Firstly, don't panic. Secondly, understand that your managed Kubernetes service provider has your back. And thirdly, do your homework. We'll talk about the same three things we've covered so far: securing the networking, securing the credentials, and securing the workloads. Kubernetes has a concept of network policies. It's a native way to filter traffic within the cluster. Although it's not enabled by default in most cases, many of the networking plugins support it. Even with a networking plugin that supports network policies, all traffic is allowed by default. Network policies support both ingress and egress traffic, and rules can be applied based on workload labels, namespaces, and subnets. Please note that if your networking plugin doesn't support network policies, you will not get any warning or error message when trying to apply network policies, but they will just be silently ignored. This is what a typical network policy looks like. It has a name. This one applies to pods that have a role label with a value of dB. It specifies both inbound and outbound rules. For inbound traffic, it allows connections from all pods that have a role label with the value of frontend on TCP port 6379. And it doesn't allow any outbound traffic. Cilium had recently made available Visual Network Policy Editor that might be helpful. Let's try to recreate our policy here. We'll give the policy a name, we'll apply it to default namespace, and to pods that have a role label with a value of dB. We're blocking all of the outbound traffic, and we're only allowing traffic from certain pods. And we get a policy here. For credentials, in addition to traditional security controls, like not committing your secrets to a version control system, we should also look into protecting cloud credentials by limiting access to the instance metadata service. This can be done through network policies as one option. As another option, and specifically when your workloads might need access to cloud resources, all major cloud service providers can now differentiate between the node and the workloads running on the node and assign roles to workloads directly. Amazon calls it IAM roles for service accounts. Google calls it GKE workload identity, and Microsoft calls it AKS Azure ID pod identity. For service accounts, by default, Kubernetes mounts service account credentials to all the pods, but majority, if not all of your workloads, don't need access to the cluster control plane, so you should be disabling the auto-mount service account token setting for your workloads. And you should use the cloud provider identity management for Kubernetes user access. For the control plane, Kubernetes API service is a critical component of a Kubernetes cluster, and limiting access to it is generally a good idea. All the major cloud service providers allow public access to the API by default, but support disabling it. And we can also use network policies to limit that access within the cluster. It's also important to keep Kubernetes up to date, and here GKE even supports automatic upgrades. Securing your workloads. There's a number of settings that you can use to lock down your workloads. For pods, most of these are defined in the container's security context. With security context, you can apply these settings to individual containers and pods. And with pod security policy, you can enforce requirements for the security context across your cluster. Another option here is Open Policy Agent. Keeping operating system on the nodes up to date is another step in preventing container escapes. And here, GKE also supports unattended upgrades if you need. There's interesting, though not widely adopted, options for improving container isolation. If you're interested, look into gvisor and Kata. When it comes to securing your images, Manage your supply chain risk by using trusted image sources. Reduce your attack surface through minimal images. Identify vulnerabilities before your attackers do by doing security scans of your images. And also, secure your applications. You may also consider security linters for your Kubernetes deployment YAML files that can alert you of common security misconfigurations. Miscellaneous things. If you're using Helm, upgrade to version 3. Version 3 doesn't have the tiller component and is much more secure in general. Logging. You should consider having your Kubernetes control plane as well as the application logs in some sort of log management and monitoring system. And protect access to Kubernetes nodes. As a general rule, if somebody has full access to one of your Kubernetes nodes, they can escalate their privileges to control the whole cluster. I firmly believe that everyone using Kubernetes in production should consider using a cloud-native security solution, and there's at least half a dozen options now in this space, including open source ones. So what are those? Cloud-native security solutions are security tools written with Kubernetes in mind and are container-aware. They can help you with many of the security configurations that I've covered. They can check your cluster configuration against security recommendations such as CIS, do image and container scanning, monitor behavior of your containers, and alert you of suspicious activity. This can be things like a shell spawned by Apache process or an unexpected connection to the Kube API server. And provide secure container-aware forensics capabilities, which is handy as often containers are short-lived and may be killed before anyone can investigate and alert. There's a number of open source tools that might be useful in your journey to securing your Kubernetes clusters. KubeBench is a CIS benchmark testing tool. KubeHunter is Kubernetes security assessment tool. KubeScan is Kubernetes workload security assessment. Falco is a rule-based runtime workload monitoring. And Trivi is container CVE scanning tools. So where do you go from here? My main recommendation is learn more about Kubernetes. Do an excellent and free Introduction to Kubernetes training. Check out these other resources and books, and I will post all the links from the last 2 slides in the Discord channel. Time for a demo. Let's put together everything I talked about so far. Before we begin, the configuration of this demo is not a good indication of what you might encounter in real life, but rather was constructed to demonstrate the concepts and threat scenarios. In this demo, we start with access to a container running in a Kubernetes cluster. First thing we do is look around. How do we know we're in a container? Let's check what running processes do we see. The small number of these is a good indication we're in a containerized environment. Let's check environment variables. Having environment variables like Kubernetes_port is a good indication we're in Kubernetes cluster. Let's check if we have access to cloud metadata. In real-world scenario, this might lead to cloud credential exposure. For next steps, we'll need kubectl, so let's install it. We're going to check the service account token. Looks like it is mounted, which is the default configuration. We're going to use the token to interact with the cluster. Let's check what services are published in the cluster. $E here means check all namespaces. So we also see Kubernetes control plane services. In the list, we see Kubernetes dashboard. Kubernetes dashboard is a web-based UI for managing Kubernetes clusters. It is not part of default Kubernetes installation and was deployed to this cluster as one of the workloads. Let's check if we can access it. To do this, we're going to use Kubernetes internal DNS service, which makes services available in the cluster as service name dot namespace name. We see that we can access the dashboard. This simulates lateral movement within the cluster. Now we would like to connect to the dashboard from outside. Let's set up port tunneling for this using our existing access to this container. We're going to use the service account token to connect. We haven't gained any new permissions in the cluster yet, but we do have a nicer interface that makes exploring the cluster easier. We see our web shell deployment. This is how we got access to the container in the first place. Now this service account also has permissions to update the deployments, which we will use to gain more privileges. We'll start by making the container to which we have access privileged. Now let's wait for the pod to be reprovisioned. Let's check we're still in the container. This IP address here is the IP address of the pod. But now we see all the processes on the host that's running the container. And we can use our privileged access to escalate our permissions to the Kubernetes worker node that is running the pod. Let's check what we see now. As I mentioned, having access to a worker node in most cases can be escalated to full cluster compromise, though it's beyond the scope of this demo. Now let's take a look at how we can fix this. We're back in the container and we'll need kubectl again. We'll also need a text editor, which isn't available in this container by default. First thing we'll do is apply a network policy to block access to the metadata service and the Kubernetes dashboard. Let's apply the policy. And now we're going to check if it worked. Metadata service is no longer available to us. And the same stands for the Kubernetes dashboard. But we still have access to the internet. Second thing we'll fix is the service account credentials. This is where the credentials are mounted. We see the secrets directory here. Now we'll edit the deployment to disable that. And check that it worked. Excellent. With two simple tweaks, we completely disrupted this attack chain. This is all I had for today. Thank you so much for sticking around. Feel free to connect with me on Twitter. I am at airman604. I would like to encourage you to join local security groups. You can often see me at OS Vancouver, DC604, and VanCitySec. You can join DC604 DEF CON group on Meetup and on Mars Slack. We have monthly meetups and are passionate about community-driven knowledge sharing. Be kind, stay safe.